Welcome to the training module on the little fuse TVS overvoltage protection devices. This module will introduce you to the various TVS device product offerings of overvoltage protection devices. You will become familiar with the key performance parameters of these devices and how they interact with the circuits they protect. We will then take a look at the little fuse portfolio of devices and discuss their selection methods. The basic strategy for any overvoltage protection scheme is to place the protector in parallel with the protected circuit. Voltage in an electrical circuit is analogous to pressure in a plumbing system. The overvoltage protector then functions as a kind of pressure safety valve. The protected circuit is not designed to handle voltages above a certain level. Forcing these circuits into conduction with high voltage can damage them permanently. The overvoltage protector, on the other hand, is specifically designed to break down at a certain voltage level and conduct large amounts of current without sustaining damage. The challenge is to ensure that the overvoltage protector will break down before the protected circuit and safely redirect the unwanted energy away from the protected circuit. In a sense, there is a race between the overvoltage protector and the protected circuit to break down in the face of a rising voltage. We must be sure that the overvoltage protector wins this race every time. Overvoltage protection devices can be divided into two classes. Clamping devices limit the voltage to a fixed level. In doing so, they absorb the excess energy of the overvoltage event as long as that event is present. TVS diodes are an example of clamping devices. Crowbar devices, once triggered, essentially short out the protected line, redirecting the excess energy away from the protected circuit. Once the overvoltage event has stopped, crowbar devices will delatch and allow the circuit to resume normal operation. Because they short out the protected line when activated, crowbar devices are used only in applications where the available power is limited, such as telephone circuits, data lines, and signaling systems. TVS devices are all clamping devices. The first parameter we will discuss is the peak pulse power rating. This is one of the most misunderstood ratings for TVS or any other device. As you can see from the datasheet excerpt here, the peak pulse power rating is 400 watts. However, on the next line down, you can see that the continuous power rating is at best 3.3 watts. Why such a large difference? The peak pulse power rating is measured during a very short energy pulse that simulates an inductively coupled lightning pulse. In this case, the pulse being used is the 10 by 1000 microsecond double exponential waveform. This is a very common pulse used in the telecommunications industry. We will look at the actual pulse in more detail in the next page. What is key to understanding here is that the peak pulse power rating will be different for every different type of pulse. The peak pulse power rating is primarily dependent on the size of the silicon chip used in the TVS diode, and to a lesser extent, the type of package used to contain the silicon chip. Because of this, peak pulse power is the common parameter across the part number series. Since the power is the product of the voltage and the current, higher voltage TVS devices in the same family will have a lower peak current rating so that the peak voltage times the peak current stays the same. Peak pulse power ratings are measured by using laboratory generated pulses that are designed to simulate the pulses caused on cables by nearby lightning strikes. These waveforms are called double exponential waveforms. One classic waveform used in telephone circuits is a 10 by 1000 waveform. That means the wave will take 10 microseconds to achieve its peak value and will take 1000 microseconds to decay to half of the peak value, specifying three things: the peak value, the rise time, and decay time fully define the waveform. Most of the time the waveform is defined by the short circuit current. Sometimes the open circuit voltage is also defined, the voltage and current waveforms may have different rise times and decay times. Notice that these waveforms are not power waveforms. They are either voltage or current waveforms. That means that in the laboratory, the voltage and the current must both be measured at the peaks of multiplied together to get the peak pulse power. The most common current waveforms are 10 by 1000, which comes from the telecommunication industry, and 8 by 20, which comes from the AC power distribution industry. Both have uses in the little fuse TVS portfolio. The next parameters we will be discussing appear on what is known as a VI curve. This characteristic curve displays the voltage and current relationships in a TVS diode. The voltage is shown horizontally and the resulting current is shown vertically. Most of the TVS devices sold are bidirectional devices. That is, they have the same characteristic curve in the positive and negative directions, so it does not matter which way they are inserted into the circuit. You can see from the graph on the left side of the curve is the mirror image of the right side, except of course that negative voltage will drive negative currents. The curve on the right shows the characteristics of a unidirectional TVS diode. In one direction it behaves exactly like the bidirectional device, but in the other direction it looks more like a short circuit. Other asymmetric TVS curves include the low capacitance offerings, which do not conduct at all in the reverse direction. This asymmetry often serves a useful purpose. They can offer specialized protection for asymmetric circuits, including reverse polarity connection protection. AC power line applications will almost exclusively use the bidirectional TVS devices. The first parameter for the VI curve is VR. Taken from Zener diode terminology, VR is the maximum continuous voltage that can be applied to the TVS diode that will not cause it to begin to conduct. VR should then be a higher number than the highest working voltage in the protected system. When designing for AC systems, remember that the peak voltages are much higher than the commonly used RMS voltages. You must also understand whenever you are designing for phase to neutral or phase to phase protection, that also affects the peak voltages. Choosing a VR that is even slightly too low can lead to overheating of the TVS diode due to continuous power dissipation. VR is measured by running a very small test current called IR through the device and measuring the resulting voltage. IR is only 1 microamp or 1/1,000,000th of an amp for most devices. Our next parameter is VBR. This is the breakdown voltage of the TVS diode. This is the voltage at which real activity begins. VBR is measured by passing a test current called IT through the device and measuring the resulting voltage. That sounds a lot like VR, and at least on this simplified graph, IR and IT look like they may be very similar. In fact, IT is at least 10 times higher than IR and is usually 1,000 times higher. Pull out any TVS datasheet and compare them. Note that IR is measured in microamps, but IT is measured in milliamps. For most products, IT is 1 milliamp. Remember that the power dissipation is the voltage times the current, so VR times IT represents some real heating energy, especially on the higher voltage products. A 500 volt TVS diode will be dissipating 500 volts times 1 milliamp, or half of a watt of power. So do not be tempted to use VBR as a substitute for VR, as you may be surprised to hear of field problems due to TVS diode heating. VC, sometimes referred to as the clamping voltage, represents the high end of the voltage characteristic curve. It is the peak voltage that will appear across the TVS device during the rated power pulse test. It is not the highest voltage that could ever appear across the TVS diode. A shorter pulse with more current will cause a higher voltage than VC to appear across the diode. Not all real-world lightning waveforms will follow the industry specifications. Nature does not read specs. Similarly, the TVS diode could be destroyed at a voltage lower than VCC but higher than VBR if it is applied to the device for a sustained period of time. IPP is the peak pulse current that is associated with the clamping voltage. Like VC, it is very dependent on the peak pulse power waveform used to characterize the TVS diode. In fact, if you look at the datasheet and multiply the IPP times the VC, you should get a number that is very close to the peak pulse power rating for that device. As we saw with the VCC rating, a TVS diode may survive a current higher than IPP as long as the duration of the pulse is shorter than the rated peak pulse power test waveform. An example of this is the 120 volt P6KE TVS diode. This is a 600 watt device and is rated to survive a 3.7 amp pulse using the standard 10 by 1000 waveform. However, the same device can survive a pulse in excess of 50 amps on an 8 by 20 waveform. The part numbers used come from a variety of industries. Because of that, there are some variations in the conventions, but all the part numbers try to indicate some combination of peak pulse power, the package used, and the voltage of the TVS device. Shown are excerpts from two different TVS device families. The top excerpt is from the SMA-J family. The lower excerpt is from the P4 SMA family. You may be surprised to learn that there's virtually no difference between these families aside from the part numbering system. Let's look at the top excerpt first. Note that the part number begins with SMA-J. This indicates the package is an SMA with a J-bend lead. The next portion of the part number indicates the VR rating. The letter C in the suffix indicates a bidirectional part. In the bottom excerpt, you can see that the part number starts with P4. This indicates a peak pulse power rating of 400 watts. The next three letters are SMA, which, like the example above, indicates the package. The number in the lower excerpt, however, does not indicate VR. Instead, it indicates a nominal value for VBR. AC is the suffix again, indicates the bidirectional part. So comparing the two highlighted parts in the excerpt shows that the SMA-J10 is a higher voltage part than the P4 SMA-10A, even though their part numbers look to be very similar. In fact, the SMA-J 8.5A is a much closer match to the P4 SMA part. Take a moment to compare these excerpts. Here are the little fused TVS diode families sorted by numbering conventions. The left-hand column shows the families that have VR embedded in their part numbers. The right-hand side column shows the TVS diode families with VBR embedded in their part number. Now let's go through these in groups of devices with similar power ratings. Here are photos of the 6 Axial package used by Littelfuse for their TVS diode products. The photos show each of the packages roughly to scale with each other. The lower two photos show the AK devices. Their leads are preformed at the factory. The only TVS diodes available in the Diode 4.1 package is the P4KE family. These 400 watt diodes often are chosen to replace low power Zener diodes that are failing in current designs due to overheating or surge failures. The Diode 15 package is home to 3 TVS diode families. The P6KE is a 600 watt family. The SA is a 500 watt family, and the SAC is a very special low capacitance design. In most applications, the capacitance of the TVS diode is of no real interest to the circuit designer. However, some communication circuits will use TVS diodes for surge protection. If the data rate is high, the TVS capacitance can become a real issue. The SAC achieves its low capacitance by having a relatively high voltage isolation diode in series with it. This combination nicely lowers the overall capacitance, but does not make a bidirectional device impossible, so all of the SAC line is unidirectional. Two device families are found in the DO201 package. Both are 1500 watt device families. The 1.5 KE family is a standard product, while the LCE family is the big brother of the SAC family we just saw in the DO15 package. The P600 package is used for the high-power TVS devices. These range in power from the 3000 watt 3KP family all the way up to the 30 kPa family. The SLD family is a special device designed for the automotive industry. It is rated on the very long 10 by 150,000 microsecond waveform because the waveform lasts over 100 times longer than the standard 10 by 1000 waveform. The peak pulse power is much lower. The AK6 and AK10 devices are unique to the TVS diode industry. These are specifically designed to compete with metal oxide varistors in protecting AC power lines. These have a peak pulse current rating, not a peak pulse power rating, and because varistors are rated using an 8 by 20 waveform, so are the AK devices. The peak pulse power ratings would be very impressive indeed. The 430 volt AK10 would have a peak pulse power rating in excess of 6 megawatts. Here are photos of 3 surface mount packages used by Littelfuse for their TVS diode products. The photos show each of the packages roughly to scale with each other. It is a cruel reality that the last letter in each DO214 package name does not match the corresponding SM designation. Because the SM designations are more logical, the package size increases with each succeeding letter. They are easier to remember and hence are more commonly used. The SMA package is home to the 400 watt devices. Notice how prominently the package type appears in the part number family name. As you may have guessed, the SMA-J and the P4 SMA devices are virtually identical. The only difference is the part numbering system used. The SMB package hosts the 600 watt TVS devices and a couple unique offerings. The SACB is the surface mount version of the Axial SAC device. Both are low capacitance designs that are useful on communication lines where the high capacitance can cause problems. This is a great choice for customers who have to run into performance issues with a 600 watt device and don't want to redesign their PC boards for a larger device. They can simply upgrade to the 1000 watt device and keep their existing board footprint. The SMC package is where the high-power surface mount TVS devices are found. Originally used to house the standard 1500 watt devices, Littelfuse stretched the SMC package to 3000 watts and now has managed to pack a full 5000 watts into the same footprint. Here's a table that summarizes the Littelfuse Axial TVS diode offerings. The first column indicates the type of naming convention used. As we have seen, some devices are named for their nominal breakdown voltage, while others are named for their reverse standoff voltage. The second column indicates the polarity configurations available. Most devices are available as either unidirectional or bidirectional devices. The low capacitance devices are a special case of the unidirectional device and are not available as bidirectional devices. The remaining columns indicate the various packages available. Here's a similar table for the surface mount devices. You may find it useful to print out these two charts to use as a handy quick reference for the little fuse TVS diode family.